And so this morning, what we will do is that we'll talk about active galaxies. But before I do that, I'll just give you a very brief introduction to galaxies because Shomak was supposed to talk, will take my place later. He's been unable to give his lecture this morning. And what you see on the first slide over here is a picture of a radio image of an optical galaxy in the Virgo cluster, M87. It's a dominant elliptical galaxy over there. And you can see, you'll soon see today that the radio images gives you information which you cannot really get at other wavebands, opens up a completely new view to our universe. I'll tell you a little bit about historical development as well. We'll talk about galaxies, we'll talk about active galaxies, and we'll talk about how they are powered, and we'll just talk at one or two aspects of it because we can't cover every aspect of it in a 1-hour presentation. First, let's start off for completeness. What are galaxies? You'd all hear of them as gravitationally bound aggregates of stars with billions of stars, it could be. And with the medium between the galaxies, between the stars, containing the interstellar medium. If you think for a moment, the size of our sun is, which is about 6,000 kilometers or so in radius, and this distance to the nearest star, Proxima Centauri, which is part of the Alpha Centauri system, you can calculate the volume of the occupied by the sun and the volume till the nearest star and take a ratio. And then you will find that only a small fraction of volume, which is less than about 1 part in 10 to the power of 20, is occupied by the stars. But the volume between the stars is filled up with the interstellar medium. And all these aggregates of stars and interstellar medium which make up our galaxy is all buried or is all sort of enveloped by a dark matter halo, which, as you know, makes up about 23% or so of the constituents of the universe. So these are the galaxies that we'll talk about. And although on a small scale, they look inhomogeneous, on the left, what you see is a computer simulation of the way galaxies would be located in our cosmic universe. And one can look at these simulations in the web. I've just given you one glimpse of it. And this central region where there's a condensation or increase in density of dark matter, that is where the galaxies and clusters of galaxies, which Ruta is going to talk about, and Shomak is going to tell you a bit more about galaxies form. Now, this is a computer simulation. This is a real sort of distribution of galaxies. This is a very small region in the sky, the 2-degree field, with what was then called the Anglo-Australian telescope. And this locates the positions of about 222,000 galaxies. And it's located in both space and time. Time as it goes backwards over here, larger redshifts, which Nassim tried to explain to you the other day. And as you go higher in redshift, you go back in time as well. And you can see that on small scales, you get all kinds of filamentary structures, very interesting shapes. And these are all due to the initial perturbations which developed, leading to formation of structures in the universe. The lower density when you go to larger redshift, this is largely sensitivity limitations. It is not really a physical effect over here. But what do the individual galaxies look like? This story started in the early part of the 20th century. Earlier, there were more of speculations starting from Immanuel Kant, whether diffuse nebulae were like island universes of our own. And there were famous debates which took place over the years. But it was in the early part of the 20th century that astronomers could make good images of galaxies. And Hubble was one of the first persons, Edwin Hubble, who classified them into elliptical shaped galaxies and spiral shaped galaxies, spirals without bars and spiral with bars. And these were generally referred to in the literature as early time galaxies and these as late time galaxies. Hubble speculated that there may be an evolutionary sequence, but today we know that the situation is far more complicated and interesting as well. Now these are just more images. On the right-hand side, you can see sharper images. Most of them are from the Hubble Space Telescope, but basically this shows you real images of the different categories. These may also have small bars in them, but these are very prominent bars, the bar type. And later, David Colliers also said they were intermediate spirals, but we'll not get into too much of details into it. Shomak will cover a fair amount of it. But just to give you an overview of what the properties are like, in astronomy, you'll find that there will always be the oddball, and there would be a gradation of properties as well. But ellipticals generally contain old stellar populations. There are also young ellipticals which form stars, but this is the overall average property that I'm talking about. So ellipticals are contain old stellar populations, which means that they're reddish in color. Why reddish in color? Because the old stars are the low mass stars. Are the low mass stars, the bright stars, the blue stars are massive stars which live relatively smaller lifetimes. Some of the heavy stars will be millions of years compared to stars like our sun, which will live for billions of years. So ellipticals generally contain old stars, whereas spirals you find often have new stars, usually have new stars. So you'll find blue patches in the spirals, particularly in the spiral arms where young stars are forming. But there are also cases where spirals look red. So that is why I keep saying that in astronomy, you'll have to be prepared that there will be a diversity in properties. And as speakers have earlier pointed out, we can't control it. We observe what we see and we make the best out of it in terms of our understanding by applications of the known physics and chemistry and now even biology that we know of to understand our universe. And lenticulars are somewhere in between. And they have somewhat like a disc kind of structure, but not really very prominent spiral structures, and they have a pretty prominent bulge. So these are the ellipticals, which look elliptical, and these are the spirals, and they may be oriented at any angle relative to the line of sight towards us. Hubble didn't quite classify all the galaxies that exist in our universe. He was more, classification scheme of Hubble was more based on the bright nearby galaxies, which are really magnificent to look at. And these are the ones which are looked at in detail by the early telescopes of that period. But later we know that the universe is much richer. And there are many more galaxies which Hubble didn't classify in terms of numbers, but which are fainter, and they also pose a lot of interesting questions, not only in terms of understanding galaxies and groups of galaxies, but the basic questions of how structures itself evolved in the history of our universe. Here are examples of irregular galaxies. These have no specific shapes, as you can see. They're amorphous. And when you go to high redshifts, you'll also find galaxies which are a mess because those are the times when they were beginning to settle down. And you'll find tadpole-like structures, comet-like structures, all kinds of structures you'll find. So this chart basically summarizes it. I'll not spend too much time on it, but just to tell you again that spirals have both young and old stars and contain irregulars have also contain young and old stars, and ellipticals have largely old stars. The spirals have a lot of gas and dust. Irregulars also have a reasonable amount of gas and dust. Ellipticals have little gas or dust. Ellipticals have little or no star formation, but both spirals and irregulars have star formation going on. So how these galaxies may have formed and how they've evolved are interesting aspects of astronomers who study galaxies. But a large number of galaxies which we have are actually dwarfs. In our own local group of galaxies, galaxies also, some occur in relative isolation in the voids in the structure formation simulations which you see or the plots of actual galaxies, but most occur in groups and clusters. Ruta is going to talk to you more about this, but even in our local group, while there are prominent galaxies like our own galaxy and the Andromeda Nebula, the bulk of it is made up by dwarfs. And these dwarfs, there are more than about 15 numbers as far as I can recall. They're very faint, and they could be very faint, and they're probably the remnants of the primordial initial density fluctuations. There are also scenarios where other galaxies may have been stripped out gas, and these too are embedded in dark matter halos, just like other galaxies. So this is just to give you a glimpse of the different kinds of galaxies. There are also what are called low surface brightness galaxies. Initially, sort of they were identified with the beautiful images which David Malin made with the Anglo-Australian Observatory. And here you can pick up very faint wisps of stars over here, which are very faint and difficult to pick up in a normal sort of the Palomar Observatory sky survey prints. They're found in relative isolation, and they have had few or if any major interaction emerging events, and they have formed due to collapse of clouds with very sort of gradual and continual ongoing star formation. But they're very difficult, and you need deep images of reasonably high dynamic range to try and pick them up. So galaxies, as I mentioned, they occur in groups and clusters, and they interact in various ways. They harass each other, they tear each other apart by tidal interactions, they merge together. Bigger galaxies swallow up smaller galaxies. You can often see dwarfs, being swallowed up, cannibalized by bigger galaxies sitting at the centers of cluster potential wells, almost surprising a galaxy at its dinner, where you can see multiple nuclei in their central regions. So the history of galaxies, their evolution and their formation and evolution, is a result of all their social interactions over time, or interactions over time, and this is and until they settle down to more placid states. But galaxies can continue to interact, and hopefully Shomak will tell you a lot more about that, and Ruta will also cover what happens in clusters of galaxies. Today, I just wanted to give you a brief introduction to galaxies before getting on to active galaxies. So if you look at the colors of galaxies, then these are the ellipticals or early type, which are more massive, you can see, and these are the disk-like or the spirals where star formation is going on, which are more blue, and the ones in between are referred to as a green valley. There is continuity, and this green valley could be spirals transiting to ellipticals, or ellipticals getting a new gas. Lenticulars could also be there. So it's a mixed bunch of objects, but basically the red galaxies or elliptical galaxies, as you can see, are more massive than the spiral galaxies. And there's observational evidence as well as theoretical work to support the view that at least a significant fraction of these ellipticals may have formed by the mergers of spiral galaxies, where during interactions intense bursts of star formation take place, and also gases stripped off by these interactions. So with that kind of brief and rapid introduction to galaxies, which will be covered in more detail later, what I will try to do is look at active galaxies today. All right. Now, what do you mean by an active galaxy, and what do you mean by a normal galaxy, say? All galaxies are active to some extent or the other, but activity can be broadly divided into two categories. One is where there is an intense burst of star formation. Our galaxy, for example, forms stars at a rate of a couple of solar masses or so per year. But in galaxies which are referred to as starburst galaxies, that could be 100 to 1,000 times larger. So this intense burst of star formation is possibly due to interactions, are often triggered by interactions, a new supply of gas, and gas being compressed to form stars. And and these activities cannot be sustained over the lifetime of the galaxy. So they are periodic events which take place, and you can probe them at radio frequencies right into the central regions, where you can see supernova remnants, follow them year after year by very high angular resolution techniques, which Desh talked to you about, and see how they evolve and build models on physical interactions of this highly relativistic plasma with the interstellar medium. There are also regions of ionized hydrogen, because when the hot young stars form, they will ionize the gas and form nebula, like the Orion Nebula, for example. It could be much brighter as well, more luminous. And these would be the free kind of emission which Dipankar spoke to you about, whereas the supernova remnants will be at radio frequencies is largely due to synchrotron emission, which is highly relativistic particles gyrating in magnetic fields. Hot gas in supernova remnants, as you saw, could be radiating free emission which are at temperatures of the order of 1,000,000 degrees or more. Now, when you look at starburst galaxies, because of the star formation, the dust gets heated up, and these are copious emitters in the infrared region of the spectrum. This is the same galaxy M82 which I showed you earlier, and you can see that they are far brighter in the infrared than at, for example, radio wavelengths. In fact, some of the more distant galaxies, which are shrouded in dust where star formation is taking place, you may not see the galaxy at all at optical wavelengths easily, and they can be picked up easily at infrared wavelengths because they're extremely luminous in the infrared. So there are whole classes of ultraluminous infrared galaxies, hyperluminous infrared galaxies, which are 10 to the power of 12 to 10 to the power of 13 times more luminous than that of our sun in just the infrared part of the spectrum were picked up by the infrared astronomy satellites and surveys. So these are an interesting class of active galaxies, which because of the high star formation rates, they also generate metals, which can propagate, which can populate the medium within the galaxies, the group medium as well, through outflows which are taking part because there's a lot of relativistic plasma or plasma which is generated and which are which is some of which can escape the galaxy. So it plays an important role in understanding the evolution of the intergalactic medium and also the evolution of galaxies themselves. But for the rest of the talk today, I'll focus on the other kind of active galaxies, which are believed to be powered by supermassive black holes sitting in the nuclei of active galaxies. So what are the characteristics of an active galactic nucleus? High energy output from the nuclei of galaxies. The energy from the nucleus can often outshine the rest of the galaxy. They could have collimated jets squirting out from the nucleus at velocities which could be close to that of light. They have very prominent emission lines with line widths corresponding to velocities, which may extend up to thousands of kilometers per second. And they could exhibit very strong variability, sometimes even 100% or so. And that can occur over a large range of timescales. Emission lines also respond to the variability of the central engine, and you can see variability in emission lines as well. And these all, provide interesting ways of probing and studying the nuclear regions of active galaxies. Now, just to give you an idea of the kind of luminosities we're dealing with, I will tell you a little bit more about these objects today, and then I will touch on just two aspects of it. One is our current understanding of how this energy might have been generated. Second thing is how fast are the jets moving. So these are the two aspects I hope to cover after giving you a brief introduction to different kinds of active galaxies and also historically to tell you how they were identified. But note that normal galaxies, for example, these are the X-ray luminosities, could be about 10 to the power of 37 to 39 ergs per second, like Andromeda M31, whereas the most luminous quasars could be 10 to the power of 45 to 47 ergs per second. So you can see to sort of recollect the luminosity of our sun, it's about a bolometric luminosity of our sun, it's a few times 10 to the power of 33. So, and all this energy is generated, for example, in a quasar right in the central region. So in the central region, the nuclear region, you have 10 to the power of 46 ergs, which is about 10 to the power of 13 suns in a bolometric suns in a region which you cannot resolve with normal telescopes. So these are exciting objects which permeate our universe. Our journey started in recognizing galaxies which are different from a normal galaxy quite early on, when spectra were taken of spiral galaxies. Normally, if you take a spectrum of a spiral galaxy like our own, it'll be dominated by the spectra of the stars. And stars have absorption lines due to absorption by the cooler outer layers compared to the photosphere. So these are characterized generally by absorption lines, although you have exotic kinds of stars which exhibit emission lines as well. So although the recognition of galaxies with a semi-stellar nucleus and emission lines were recognized quite early on, the importance of it really was recognized when Carl Seyfert drew attention to a number of such galaxies from a survey of the spectroscopic survey of spiral galaxies. And these lines could be resolved. And initially they were hundreds of kilometers, but we know that they can range up to thousands of kilometers per second or so. The Seyfert galaxies are hosted by spiral galaxies and spiral galaxies. And then they are broadly spectroscopically classified into two categories, namely Seyfert 1 galaxies, which have narrow lines with widths up to a few hundred kilometers per second, and broad lines, with widths which can range up to 10,000 kilometers per second. And you can see that the broad widths imply that the line emitting clouds are moving around with very high velocities. Okay, just give me a moment's break. I'll just sort of have to attend urgently. Sorry, there was something I tended to attend to. Whereas Seyfert to galaxies show only narrow lines. So if there is time, I'll address this in the question period time, but now we will just remember it as a spectral classification. And broad line widths also mean that the line emitting clouds are moving around with velocities of that order, which means that there is a massive object which is governing this motion. Okay, these are just images of spiral galaxies. They can occur in groups, they can occur in relative isolation as well, and but they're generally hosted by spiral galaxies. Now, just to recap what I told you earlier, that this is a normal galaxy. This is a spectrum which I picked up from the Sloan Digital Sky Survey. What you can see are generally absorption lines. And you can see that you contrast this with that of a Seyfert 1 galaxy. Okay, you can see the striking differences in the spectrum. And you can see this broad component of H alpha over here, H beta over here. In addition to the narrow lines, you can see the H alpha and the nitrogen 2 lines over here. You can see oxygen 3, which is a forbidden transition, which is often seen in these galaxies. This is a Seyfert 2 galaxy, where again you can see the emission lines, which are all narrow. The broad component is missing. For some reason, the broad component is not observed in Seyfert 2 galaxies. And if there is time, in the end, I will come to that, but I'll just skip it. And this is a galaxy which is a starburst galaxy. And a starburst galaxy is basically from regions of ionized hydrogen. So there's recombination lines which take place. And you can see, but they're narrow. They're not moving around at tens of thousands or thousands of kilometers per second. But these are more characteristic of regions of ionized hydrogen. So, so this is sort of a brief summary of this category of galaxies called Seyfert galaxies. They came about by trying to do a spectroscopic survey of spiral galaxies, and which seemed to show galaxies, or which showed galaxies with semistellar nuclei and and uh, very prominent emission lines. Seyfert 1 with broad emission lines, which can go up to tens of thousands of kilometers per second, thousands of kilometers per second, whereas the narrow lines are in Seyfert 2s, which have hundreds of kilometers per second. Radio images actually showed all kinds of interesting structures where Seyfert galaxies can have narrow collimated jets. They're usually small, confined within the dimensions of the host galaxy. And when you image them with in molecular cloud or neutral hydrogen, you find all evidence of tori or disk-like structures in the central regions of these galaxies. But the most luminous objects actually came about from the early radio work. You see, when people made surveys or astronomers made surveys, the initial surveys were done at Cambridge and in Australia at low frequencies. And when they found these blobs or patches on the sky, they wanted to find out, hey, what is emitting these radio waves? So the natural step was to try and see if we can find optical counterparts to these objects and see if the radio emission is associated with any kind of optical object. And as we discussed during one of the lectures, that you really need high resolution if you were to get identifications of more distant objects, because within the low resolutions of that period, there would be many optical objects within that beam. So you needed high resolution to be able to identify more distant objects. But for relatively nearby objects, because the angular size of the galaxy is also large and the radio beam is also large, you had a fair chance of saying that, hey, hold your heart in your hand and say, hey, these must be associated. So some of the early galaxies which were identified were Virgo A, Centaurus A, Fornix A, Hercules A, and also Cygnus A, which is a little bit more distant. And one needed, and then later on, when one began to observe them with high angular resolution, one found that, hey, these are not just confined to the optical galaxy. These could be, these consist of lobes of emission with the optical galaxy in between, okay, which is this little spot over here. And an image of an optical, a somewhat disturbed optical galaxy is sitting over here, and you find evidence of relativistic plasma squirting out from the active galaxy over here to distances which could be hundreds of kiloparsecs. Today we know that that the largest structures or largest sizes as projected onto the plane of the sky is about 4.57 or so megaparsecs across. So a million parsecs across, and one parsec, as you will recall, is about 0.26 light years. So these are some of the largest structures which are known. These are among the most luminous objects known in the universe. And they pose a number of interesting and challenging questions. One is related to the generation of energy. One is related to the collimation of energy. The other is to actually look at the effects of the jet on the galaxy itself, a term which has been coined called feedback, and how the evolution of the galaxies themselves are influenced by the formation of such structures. Now, when we take a volume of space in a volume of and look at all the galaxies within it, we find that only about 10% of them have such luminous radio sources. So are these intermittent? Or what triggers, if they're not intermittent, do all galaxies go through such a phase? Or if they're not intermittent, what is it? What are the physical conditions that lead to the formation of these double-lobed radio sources with extremely high luminosity? So these are questions at the forefronts of trying to understand radio galaxies. And these are sort of more images of them. I will not get into details of structures because this is more at an introductory level. But you can see that this is an image where the optical galaxy is overlaid on the radio image. All colors are false over here. And you can see them going well outside the radio galaxy. Some, as you can see, have diffuse plumes. Some have bright hotspots at the outer edges, as in the case of Cygnus A. I will not get into details of Van Rayleigh classification, but basically these are the host galaxies are elliptical galaxies over here, as unlike in the case of Seyferts, which are largely spiral galaxies. And this is also a superposition of it. And you can see all kinds of interesting structures here. You can clearly see the signature of a jet, which is one-sided, hotspots at the outer edges, hotspots at the outer edges where the beams interact with the external medium. But there are lower luminosity sources where the jets just diffuse out into plumes of emission. So there were a lot of exciting classes of objects which were trying to, which one identified in the universe by trying to look at optical counterparts of radio sources. Now let me just sort of jump to the next class of objects which I was going to talk about. And these are the quasars, which many of you would have read about. And this also was found by trying to find optical counterparts of radio sources. And these were 3C sources, which were bright sources in the sky. And when they tried to identify this object, it is more distant than the galaxies which were identified. One needed far more accurate positions than what was possible at that time. And at low frequencies, as you would have recalled from Deish's lectures, that resolution is given by lambda by d. And with the low frequencies which were in vogue at the time, and the diameters of the dishes, the angular resolutions are rather poor. So you needed pretty high angular resolution to be able to say, hey, that's where my source is, and I can identify the object reliably. So that opportunity was provided by this radio source called 3C273, which was getting occulted by the moon. And since you know the position of the moon very accurately, and this creates a diffraction pattern which gives you the structure of the source as well, or you can infer from it by an inverse transform, and you could measure the position very accurately. In fact, these measurements were done in Australia by Cyril Hazard and his collaborators, and they took great precautions to minimize any radio interference that may affect their operations, observations. And also I understand that, the data were recorded in 2 different tapes and sent by 2 different planes to make sure that the data was not lost. And this is because, the occultation, you cannot tell the moon to go here or there. You'll have to live with the part of the moon and what gets occulted. And when they found the position of this object accurately, they could realize that it was a star-like object. But the surprise didn't stop over there, because when they looked at the spectrum, they found that it had very prominent emission lines. And initially they had great difficulty in trying to understand the emission lines, because when they tried to compare with lab emission lines, it didn't match with anything that they were readily familiar with. But that was because they had not allowed for redshift. And it was Martin Schmidt who recognized that if you shift the lines by 0.1, by a redshift of 0.158, where lambda observed is equal to lambda emitted, which had been the lab frame multiplied by 1 plus z, then they realized that it exactly fitted the Balmer spectrum of hydrogen. So this was the identification of an object which was which was um, which was outside our galaxy, looked star-like, and given the luminosity, you can calculate the distance and showed how energetic and highly luminous these objects were. There were some astronomers who doubted the cosmological interpretation for redshifts of quasars because of the very high luminosities that they implied, and there were challenges in trying to understand this high luminosity. But today, I think almost everybody believes that the redshifts are largely cosmological, and there are reasonably good explanations for the energy that they generate. So this was another class of active galaxies which radio astronomy helped unravel or help discover. And from very early on, people asked the questions that, hey, it is star-like, but is there a galaxy around it? Are we not able to see the galaxy around it because the star is very bright? The nucleus is very bright. Just as you don't see the stars when the sun is out, are we not being able to see the galaxy because the nucleus is very luminous? And some early ground-based observations suggested that it may be the case for the odd case or two, but this was really established with the observations of the Hubble Space Telescope. You not only required high angular resolution because you don't want the image of the central prominent nucleus to burn out all the surrounding galaxy, or not be able to resolve the galaxy, but you also needed high dynamic range. So a combination of high dynamic range, high resolution, and clever image processing revealed that almost all galaxies in the direction of which you can see, you should be able to see the surrounding galaxy, one could see it. Actually, even in the early observations of the Hubble Space Telescope data analysis, they goofed because of the difficulties in trying to bring out faint emission. But later, with more careful and better image processing algorithms, one was able to bring out these galaxies in almost every quasar. Then when you could do that, you found that they were not only spirals, they were ellipticals, they were interacting systems, and there was a whole host of them. So the quasars can be hosted by either ellipticals or spirals, although many of the radio loud tend to be elliptical galaxies. So this is just, and again, just as in the galaxies, if you took a volume of space in the universe, looked at all the quasars over there, you would find that again about less than about 10% of the 10% is a ballpark number, would be extremely loud or luminous in the radio. Most are radio sources, but are weak, or people use the term radio quiet for them. This dichotomy has also been sort of looked at more critically. Some have questioned it, but there is no doubt that there is a tail of very luminous radio sources, and most of them are very weak or radio quiet. So this is the same questions which arose when understanding querying that why only 10% of ellipticals are radio loud. It is a question which we have not answered satisfactorily as yet, and it is still in the forefront of research. Now, let me try to introduce to you to the last class of objects called the BL-Lacerti type objects. So the zoo of active galaxies is quite large. I've just picked up a few which will illustrate the importance that radio astronomy has played in trying to identify these objects. And these are amongst the most exciting and in the zoo of active galaxies in terms of applying known physics to understand what is going on as well. So BL-like objects also came about by trying to find optical counterparts of radio sources. Now, the term BL-like has come about because this particular object was earlier classified as a variable star. And variable stars are usually named by the name of the constellation in which they occur. In this case, it is the constellation Lacerti, and they have combinations of letters A, A, B, AC, and I think some combinations are left out. These are just historical reasons, and when they run out of all two-letter combinations, they call it V and put a number after it. So this was classified as a variable star in the constellation Lacertae, and this was a radio source which is cataloged by the Vermilion Radio Observatory. Accurate position was measured later, I think, by the Texas Observatory as well. And then they tried to identify the optical object. When they found the optical object, they found it to be associated with this variable star. Now, then the next logical step would be to take a spectrum and find out, hey, what kind of a star is this? Because usually stars are not so luminous. It is true, as Divya mentioned, that the sun is extremely strong for us. But if you to calculate the absolute luminosity, it's really very small. It's just an ordinary star. So if it was really a star-like object, it was very interesting to find such a luminous radio source associated with it and see what kind of an object this is. Then they took a spectrum. And when they took a spectrum, they were rather surprised because unlike a quasar, which had prominent emission lines, which one got used to by now, that this one hardly showed any lines at all. They were continuum, they were strongly variable, they were strong radio sources. Questions, are they galactic? Are they extragalactic? The first hints about them being extragalactic came from their distribution in sky. Galactic objects would normally be confined to the plane of the galaxy, largely, although globular clusters are more uniformly distributed, but largely stars are in the plane of the sky. But these objects were uniformly distributed all across the sky. Then there were some which showed very weak lines, absorption and emission lines. And when you saw them, you could find out that they had a redshift and that they were outside our system. So these are some of the very strongly variable objects in the sky. They're also very luminous. They're strong radio sources. And just like quasars, for example, if radio astronomy had not developed and X-ray astronomy developed earlier, they are also copious emitters in the X-ray, and you would actually pick it up quite easily. Here I've just shown you again the collage of the spectra of what we have discussed so far, that the B and lag type objects are extremely luminous, but they have almost a continuum spectrum over here. This is a mean quasar spectrum, broad emission lines, as well as narrower ones, but usually dominated by strong, broad emission lines. Then you have these are generally elliptical galaxies, mixture of ellipticals and spirals. And this is the spectrum of a normal galaxy where you can see largely absorption lines. There may be diffuse emission lines from nebulae in the galaxy, but largely absorption lines from the stars. Seyfert galaxies, again, you see prominent emission lines. Seyfert 1s have very broad lines and narrow lines. Seyfert 2s have narrow lines. Radio galaxies, too, a small fraction of broad lines, but generally narrow emission lines, a fraction of broad lines as well. So the story of broad versus narrow is something which I don't know if I'll have time to address, but if there is time, we'll do it later. So you can see the exotic variety of active galaxies that exist in our universe. And some of them are more variable than others. The BN-like objects and a subset of quasars called the optically violently variable quasars are collectively referred to as blazars. These could vary over a night. Unlike, for example, our sun varies very slowly. And most of these radio sources, for example, very slowly. The large scale emission, they don't vary at all. Whereas these quasars, the nuclear object, the violently variable quasars, and the BL-like objects exhibit very strong variability in both total intensity and polarization as well. Now, let's ask ourselves, giving you just a brief introduction, just an overview of the kind of galaxies which exist in our universe. Let's just have a look at the kind of numbers about what is the total energy content in the lobes of these radio sources, and a brief look at how is this energy likely to be generated. Okay. I've been rather rapid, but the thing is that these are largely pictorial, and the slides will be available to you, so you can look at it at your leisure. And also, I've given references in many places, so if you can go back to the links and have a look as well. Now, I'll not get into the details of how that is calculated, because of lack of time, but I'll just tell you the numbers that are involved. Okay. For example, the Cygnus A radio galaxy, which is one of the more luminous radio galaxies in the universe, that's at a redshift of 0.0561, which in our modern cosmology implies a distance of 250 megaparsec. And given the angular size which you can measure and the angular diameter distance which you can measure from the redshift, you get a size of about 140 kiloparsecs or so. To put this in perspective, for example, the distance of the sun from the center of our galaxy is about 8.5 kiloparsecs or so. Now, if I look at just the radio frequency, the radio emission from it, the total radio luminosity, 10 to the power of 7 hertz is about 10 megahertz. And whereas Desh and others and I have told you earlier that radio observations are possible, not possible from the Earth below about 10 megahertz because of the ionosphere, which doesn't allow lower frequency radio waves to come through, but you could observe it from outside the ionosphere, to about 10 to the power of 11 hertz. This is a power law spectrum. So higher the energy you go, the intensity decreases, the flux density decreases. And you can calculate the total integrated luminosity is of the order of 10 to the power of 45 ergs per second. And these numbers could well exceed the bolometric luminosity of a galaxy. And all this luminosity originates from the central nucleus over here. So if you make estimates of the magnetic field and the total energy, okay, the total energy is of the order of 10 to the power of 60 ergs or more. And the fields are small. They could be about 10 to the power of -5 or even -6 Gauss in the diffuse extended lobes. So you can see that it is micro Gauss levels to maybe 100 micro Gauss in the most compact features. And it is in this weak field that is high energy electrons are sort of moving at relativistic velocities to give you the synchrotron emission that you see. Now, how is this energy generated? So because of difficulties in generating this energy in the early years when quasars were discovered, particularly at higher redshifts than the galaxies, today we can detect both galaxies as well as quasars to the furthest reaches of the universe, that people speculated that the redshifts may not be correct. And because the kind of energy sources that one talked about, whether it be chemical or nuclear, it was very difficult to understand this generation of such huge quantities of energy from a very small volume of space. So now let's go a little further and see what the current scenario is in terms of the energy that is being generated. It is now widely believed, and there is reasonable evidence to support this as well, that this is due to accretion onto a supermassive compact object. Now, if you consider a proton of mass m falling from infinity, then from the conservation of energy, as it comes closer, it will be more strongly gravitationally bound and kinetic energy will build up. Now, at a radius r equal to r, when it hits a hard surface, like the surface of a neutron star you listened to earlier this morning, the particle will come to an abrupt stop. And the kinetic energy will be radiated away. If it's a lump of matter, some of it will get into internal heat as well. And this is the kind of energy which can power for the most compact objects at X-ray sort of wavelengths. If I were to sort of talk about it in terms of the accretion of matter, I could put it as a luminosity of half dm dt, the rate of accretion of matter, into VFF squared, and as well as dm dt over here. And substituting for the value of VFF squared and the Schwarzschild radius of an object of mass m, I could write down the luminosity as half dm dt c squared rg upon r. Now, if I were to sort of look at this equation and I define an efficiency which is defined as half rg upon r, rg is the Schwarzschild radius of an object of mass m, which is given by 2gm by c squared, and dm dt is the rate at which mass is being accreted. Then if I look at a white dwarf star, which is the end product of the evolution of a star like our sun, then its typical radius is several thousand kilometers, you'll get an efficiency of about 3 into 10 to the power of minus 4. You might say, what is the big deal over here? Because from nuclear processes in the sun, the efficiency is about 0.007. This may not be something you want to write home about, but if you make the object more compact, like a neutron star, you can see that distance is much smaller. Radius is about 10 to 15 kilometers. 10 kilometers is a more canonical value that often gets quoted. Then you get half Rg upon R is about 0.1. So you can see that this becomes a very efficient process for extraction of energy, of gravitational potential energy, as object gets accreted onto a massive object. So you could do even better, I suppose, if matter is accreted onto a black hole, except that the black hole doesn't have a hard surface. So if it was radially falling in, it will just go beyond the event horizon and it will be sucked up by the black hole, which would only be characterized by its mass and angular momentum charge. Okay, but what happens is that material starts off with some angular momentum initially. So it doesn't fall straight away into the disk, into the black hole, and its rotational energy increases as it goes closer and closer into the black hole. Centrifugal forces will stop it from collapsing in a direction orthogonal to the rotation axis, whereas it will collapse in the along the rotational axis, leading to the formation of a disk kind of structure. And viscosity in the disk will redistribute the angular momentum, making some of the material spiral inwards while spreading some of the material outwards. And viscosity also acts as a frictional force which dissipates heat. So more detailed calculations of extraction of energy in a Schwarzschild black hole is about 0.06, whereas a maximally rotating Kerr black hole is about 0.426. So you can see that extraction of energy by accretion onto a supermassive black hole provides a means of trying to extract energy from this accreting mass. Now, can we go on and increase the mass accreting rate to achieve as high a luminosity as you like? And the answer is no. The answer is no, because once you generate more energy, there will also be radiation pressure from the surface, and radiation pressure will start to begin interacting or counteracting the effect of gravity. So if radiation pressure increases the effect due to gravity, then you'll not be able to sustain the accretion of matter onto it. And the material falling in is electron, proton, plasma, ionized plasma, large electron, proton, plasma. So Thomson scattering is a process that is at work over here. I will not go into detailed derivation. You can have a look at it in the slide. But when you equate the force due to gravity to the radiation force over here, where Thomson scattering plays a role, the number of photons is governed by the luminosity and at a distance r from it. You'll find that these r squareds cancel out, and the luminosity, the maximum luminosity that you can get, is just depends on the mass of the object. The rest are all fundamental constants over here. So the more massive the object is, the more luminous, the higher the luminosity that you can get out from the object. So if you have this is the expression in terms of units that you can relate to. So you can see that if you had a supermassive black hole over here of about 10 to the power of 8 solar masses or so, that you could get a luminosity of about 1.3 into 10 to the power of 46 ergs per second, which is in the ballpark of the luminosities that we talked about earlier. This is putting the same expression in terms of the Schwarzschild radius. You'll often meet this in the literature, but basically it is the same sort of expression, except that this is put it in watts rather than ergs per second. So you have a 10 to the power of 7 factor absorbed over here. You can also calculate the luminosity of the object, because a black body would radiate most efficiently. Radiation be emitted most efficiently when it radiates like a black body. So you can equate the Eddington luminosity to the Stefan-Boltzmann's law and get an expression for the temperature. So if you do that, you'll find that for solar mass neutron stars with a radius of about 10 kilometers, temperatures are in the region of 10 million degrees Kelvin or so, and then you will get radiation in the X-ray part of the spectrum. For white dwarfs, radii are larger, so it is more in the ballpark of about 10 to the power of 5K or so, which will be in the ultraviolet region of the spectrum. For supermassive black holes, of 10 to the power of 8 solar masses or so. Okay. Now here again, the temperatures are in the ultraviolet region of the spectrum. And that is because the radius that you're talking about, which is the Schwarzschild radius, the last stable orbit is at about 3 times the Schwarzschild radius in a black hole. And then if you look at this expression over here, the radius at which energy is being deposited is also increases with the mass. So the more massive the black hole is, your Schwarzschild radius and hence the radius of the last stable orbit is also larger. So for supermassive black holes, you expect a bump in the ultraviolet region of the spectrum. And this is actually observed in the spectra of quasars, which is referred to as a big blue bump in the continuum spectrum of quasars. And this probably, okay, I'll just briefly mention it, that from the Schwarzschild radius, you can also estimate the time scale of variability that you expect, because it should really be 3 times the Schwarzschild radius over here, but this is just to give you a kind of ballpark number that that you can go and estimate from the time scale, from the time scales of variability that you observe, at least some limits on the distances that you're talking about in the center of the black hole, because you can't really observe them or image them with the kind of resolutions which you have. It's only recently that the Event Horizon Telescope has been able to image just one galaxy, M87, which is a relatively nearby object. So you can see if RG is small, then the timescales of variabilities will be small. If RG is large, as in the case of supermassive black holes, then you'll find that the timescales are larger. So once you know the timescales, you can estimate the distances, and from the velocities, you can also go and estimate the mass of the black hole. And when you do these by these causality arguments, you get masses which are very similar to what is estimated by other means. So I'll just spend the last 5 minutes, 5 minutes or so, talking about speeds, okay, of the jets, that we have a reasonable explanation for the generation of this large quantity of energy by accretion onto a supermassive black hole. I've not touched on the formation of jets, the models themselves, but magnetic fields and rotation are believed to play a very important role. But let's just ask a very basic question as to what is the speed at which one is moving? Are these jets moving out? I kept saying that they're moving at relativistic speeds, but can we actually try and put a handle on that number? We can put a handle on that number by doing something very simple, which is actually you just measure velocity by identifying a feature and monitoring that feature year after year after year and seeing how much it has moved. Okay, but even if it is moving at relativistic speeds, what is going to happen is that it'll move, the actual angular displacement will be very small. It will be really at the milli-arc second levels. So at the milli-arc second levels, you need very high angular resolution. The very long baseline techniques which were spoken about earlier. Now, from your understanding of Fourier transforms and also from the techniques lectures, you'll realize that when you have very high resolutions, you will actually resolve out or not see the diffuse extended emission, but you'll only pick up the really compact emission at the nuclear regions of the sources. So high resolution means being blind to the diffuse large-scale emission, whereas low resolution means that you cannot see the small-scale structure. Now, if I go and make a map, for example, the quasar that I talked about, 3C273, with milli-arc second resolution, I will go and I can pick up some peaks of emission over here. This is the nuclear or core component, which is the brightest. The extended emission I don't detect in this VLBI scale emission. Now, if I look at these two knots of emission, say I measure it in 1 year, then I measure it 6 months later, 1 year later, 2 years later. And that has been done for decades now for many objects. But in the early years when this was really pioneering effort, you can see in the 70s, this was for 3C273, this is for another quasar from the 3C sample. And they looked at how much it has traveled. And from the distance of the object, you can convert that to linear distance. And from the time which has evolved, you can go and calculate what the velocity should be. You can apply your corrections due to the redshift, etc. And you find velocities which are much greater than that of light. So initially people, radio astronomers were comparatively few in number, at that period of time compared to the optical astronomy community. And these were sort of doubts were cast. Doubts were also cast on the interpretation of the redshift. So the distances were probably wrong, or the distance traveled was wrong. But it was in a very early work by Martin Rees, which laid the basis for understanding this in terms of just very simple basic physics and geometry. These are other examples as well. This is of the galaxy M87 jet, which I mentioned earlier. And now today, when you monitor this motion, you not only see velocity of advancement at superluminal speeds, but you also see acceleration, you see changes in direction, you see all kinds of interesting motion, which one tries to interpret in terms of what is going on at the nuclear region. But let me just give you a very simple heuristic kind of argument as to how we understand this, and how it is very easy to understand this. So let's say this is the quasar, the filled dot over here, and it is emitting this plasmon, which is traveling outwards at a velocity v. And say when this plasmon was over here, it gave out a wavefront of light which is coming towards you. The wavefront of light will travel at a velocity of light towards you, and this is moving outwards at a velocity v. So now let's say at a time t later, it emits another pulse of emission, okay, another wavefront, which you're going to detect. Now, how much does it travel over here? It travels a distance v into t. And what are you going to measure in terms of the distance traveled in the sky? You see everything projected onto the plane of the sky. So the distance which you see traveling would be delta d, which is equal to velocity into time into sine phi, where phi is the angle at which the jet is coming towards you, the observer. What is it? How much has it traveled in this direction? It is Vt cosine phi. This signal has traveled Ct. All right. This signal is emitted when the distance traveled is Vt cosine phi. So what you have is the time difference which you see between these two wavefronts, delta t, okay, would be this distance divided by the velocity of light. Okay. And you can see this distance is nothing but Ct minus Vt cosine phi. And the time would be the distance divided by the velocity of light. So what is happening is that now you take this distance, which is Vt sine phi, divided by distance divided by time will give you the velocity. So you divide this is t, you take out c, it will be 1 minus v by c cosine phi. And with a little bit of algebra, you'll be able to show that the apparent velocity which you get is beta sine phi divided by 1 minus beta cosine phi. So in terms of physical understanding, what is happening is that your time is getting squashed over here because the wavefront which it emitted earlier, the plasmon is almost keeping up with it. So if the velocities were very low, this would not happen. If it is going at a perpendicular angle to the line of sight, it's not going to happen. If it is going away from you, it's not going to happen. It's only going to happen when it's coming towards you with a high velocity at a small angle to the line of sight towards you. Okay? And you can put in numbers over here that suppose it is 0.99 C and put an angle of 5 degrees, you'll get beta apparent of about 6.3. Okay? So you can see that just by simple geometry and the fact that these are moving at relativistic speeds, you can understand superluminal motion quite easily. And and you can play around with this. You can see at what angle this gets maximized, what is the most likely value of phi, and you'll find that these are usually occurring at small angles to the line of sight towards you. You can see straight away if you put phi equal to 90 degrees over here, that sine 90 is 1, cos 90 is 0, you'll get beta apparent equal to beta. And if it is going away from you, the sign will change and you're not going to get superluminal velocities. So you get superluminal velocities when jets are coming towards you. From the most probable angles, etc., you can estimate what the angle of inclination and what the velocity is. At these high velocities, what also happens is that the emission gets Doppler boosted. So that is why you're seeing these jets, which I showed you, to be one-sided, because the one which is going away from you is Doppler diminished. So these ones, the intensity gets enhanced due to the Doppler effect, where there's a shift in frequency, shift in time, solid angle of emission over which the radio emission is emitted and observed are different. And you can take the ratios, and the ratios will be 1 plus beta cosine phi upon 1 minus beta cosine phi n to the power of 2 or 2 plus alpha, 2 or 3 plus alpha. That is a bit model dependent. And if you take velocities of the order of c, angle of inclination is about 20 degrees, you can get very large factors of flux density ratios. And because of observational limitations, you can't see the receding jet in these cases, as well as in the jets which I showed you earlier. But if you had very low velocities, then you would pick up the jets on both sides. And that is what is believed to be happening in the cases of these low luminosity jets, where you see emission on both sides, whereas these more luminous jets, the velocities are higher, and because of Doppler effects, you see jets on only one side. So I will stop here. I probably overshot by a few minutes, and I'll be happy to take any questions. Thank you.
Sir, why don't spiral galaxies generally emit radio jets?
Actually, the question is related to what really triggers radioactivity in the central region. We know that accretion is a viable process, and and from the masses of the black holes, which we have been able to determine that in both spiral galaxies and elliptical galaxies, we know that the masses are commensurate with the luminosity that is observed if the accretion rate is about 1 to 2 solar masses per year, even for the most luminous objects. For less luminous, it depends on the mass of the black hole and the accretion rate. Now, the question is that these black holes exist in all galaxies, okay? In all galaxies with a bulge. Okay, we have been able to infer existence of these black holes even in galaxies which don't have these prominent jets and radio lobes. And that is true of spirals as well as ellipticals. So there is a process by which radio emission gets triggered. And that is something probably one suspects that it probably has to do with the magnetic field and the spin of the black hole, and also the availability of fuel. So with these factors being satisfied, that then radio emission gets triggered. But what exactly it is something which is not absolutely clear cut, although there are processes and scenarios by which rotation and getting rotational energy from the black holes and collimating it via the magnetic fields, or in some cases, a very thick accretion disk with a funnel leads to the formation of jets. But the exact process as to why a particular radio jet gets triggered is not very clear. That is true of spirals as well as ellipticals. Not all spirals are Seyferts. Only a small fraction are Seyfert galaxies which have these radio jets. But any spiral galaxy with a bulge, also spiral galaxies have a bulge. In addition to the spiral arms, they also have a black hole sitting in the center. And the properties of the bulge are intimately related to the properties of the black hole, because there is a very tight and close relationship between the mass of the black hole and the velocity dispersion in the bulge. In the elliptical galaxy, it is the entire galaxy itself, whereas in spiral galaxies, it's a bulge of the spiral galaxy. So we know that the mass of the black hole is related to the overall properties of a galaxy, which has probably to do with the way galaxies evolved over its lifetime. But exactly what triggers a radio source is something where there are models and ideas, but putting both observations and theory together, I don't think we have a complete answer as yet.
Okay, thank you, sir.
Any other question?
Resource constraint, and you can make an appeal to case they would consider.
Are there any other questions?
Hello.
Hello.
Any reasons behind
Hello.
lenticular galaxies having like less amount of star forming region?
Okay. Actually, lenticular galaxies, it depends on what their origin is actually, okay? For example, if lenticular galaxies are really spiral galaxies which have lost their gas because of because of interactions. Okay, they're basically disk-like galaxies, as we mentioned earlier, without the presence of strong styrons, obvious gas and dust. Okay, the thing is that it is possible that they are evolved from spiral galaxies, or they could be also elliptical galaxies, which have acquired some amount of gas and dust due to interactions. But the gas and dust content is not commensurate with those of spiral galaxies where a lot of star formation is going on. In these spiral galaxies, for example, when you observe them at millimeter wavelengths, you can also see copious amounts of molecular clouds in the spiral arms from which new stars are forming. They are basically the stellar nurseries. So they're sort of intermediate between them in terms of both gas and dust content, although there are exceptions to the general rule. But but uh, but the thing is that there could be different routes, as I just mentioned. Okay.
Thank you, sir.
Hello.
Yeah, go ahead.
Yeah. So, if a galaxy has an active galactic nuclei residing in it, and but the jets are not in our line of sight, so can the study of star formation in that galaxy give some hints whether the galaxy has an active nuclei or not?
Actually, what the thing is that if there is a very prominent jet in a galaxy, that you one should be able to observe it. Okay, it is true that if the jet is pointing right at you, okay, right at you, it will be more difficult to discern it than if it is at a larger angle towards you.
Okay.
Probability of a jet exactly lying at the line of sight and a straight jet is very small. And also, if it is also the jets, you'll notice when you look at the images that they wiggle around, probably due to precession of the central region. They could also be interacting with the environment around them, and and so I think if a jet exists, you should be able to see them with today's telescopes. All right. Now the question is, what does it leave telltale signatures in the star formation? So the thing is that jets can influence star formation in various different ways. Okay, for example, there are cases observationally as well, where, for example, to form stars, you want a molecular cloud or you want a gas cloud to collapse. Now, the momentum flux density in the beam of a jet can uh, can uh, can trigger star formation by triggering collapse of a gas cloud to form stars. There's a very famous object called Minkowski's object. You can Google it and read a bit more about it, where you can see evidence of star formation, which is triggered by a jet, which seemed to lie on the part of the jet and is interacting with it. Okay, there are also cases where, for example, you see enhanced optical emission along the length of the jet, and this enhanced optical emission along the jet is perhaps due to stars, at least a significant component of it, which is star formation triggered by the jet. But the reverse can also happen. For example, you want to form stars. So when clouds collapse to form stars, you need gravity to be important. So you need dense clouds, but you also need the internal pressures to be low, because otherwise, if the internal pressures are large, then the cloud will find difficulty to collapse to form stars. So there was a condition derived by James Jeans very early on called the Jeans condition, where you need gravity to overcome internal forces due to temperature, kinetic pressure. Now, for example, if the jet has the effect of heating up the cloud, then also you'll find that star formation may be sort of hampered due to the jet, which is sort of heating up the cloud. So both these effects seem to play a role, and one sees effects of it in different galaxies. But obviously, there is a region of parameter space where cloud where star formation is triggered, and there's also a region of star formation where star formation is hampered. For example, when one does numerical simulations of these low luminosity jets, which are not very well collimated, passing through the interstellar medium of the host galaxy, you can see a significant portion of the ISM being affected by the star formation, by the jet going through it. temperatures rise, they become more turbulent, and so these are regions where star formation be hampered. So you can infer there is a positive feedback. There is a feedback of star formation by the jets, both positive and negative. But you don't need them really to look at the jets because the jets are more easily observed directly itself. And if you just saw enhanced star formation, it doesn't necessarily mean that there is a jet. It could be a region of star formation triggered by an interaction as well. So you can see both effects, but jets are today's technology enables you to detect jets at a wide range of wavelengths. And radio is particularly good for looking deep into the nuclear regions because they may be not visible in the optical, for example. Okay.
Yeah, thanks. Because I had somewhat a different interpretation that if there is an agent, then the star core collapse won't will be restricted by the influence of the gravity of that agent. Uh,
Actually, both effects are sort of seen observationally. Yeah.
okay.
But one needs to delineate the set of parameters which will enable stars to collapse, gas clouds to collapse triggered by the jet, and also cases where star formation is hampered. Both can occur actually.
Okay. Yeah. Okay. Thank you.
Sir, like whenever we talk about active radio galaxies, the jets which we can see, like in most of the case, those are symmetrical. And in those symmetrical jets, like sometimes one jet is like comparatively brighter compared to the other one. So can it be due to the environment in which the galaxy lies, or is there any other reason behind it?
Okay, let me just show you. Yeah, let me show you. This is a jet which is reasonably symmetric, and this
Yeah.
is a jet which is reasonably symmetric. This is a jet which is asymmetric. Okay, and I showed you a picture later. Later, okay, this is the color I was looking for. You can see very asymmetric jets as well as
No,
very symmetric jets,
no,
right?
sir, I'm not talking about this. Like the jets are both are symmetric,
Okay,
but the brightness of one is comparatively low than that of other.
okay, okay,
Yeah.
okay. You see jets on both sides, but one is more asymmetric than the other. Okay, there are the most likely okay. Let me tell you what the physical processes that can play a role over here. Okay, now we talked about relativistic motion of the jets. Okay, and now if a jet is moving at a relativistic velocity, then what you will find is that the one which is approaching you, the flux density would be enhanced due to relativistic effects, Doppler boosting, and the one which is going away from you will be Doppler diminished. In the case where the angle of inclination is very small, you may not see the opposite jet at all, right? Opposite jet at all. Whereas in cases where the angles of inclination are large, then the brightness ratio or the flux density ratio would be more moderate, and you may pick up a jet on the other side as well. For example, in this radio galaxy Cygnus A, both the jets are weak, but the more prominent jet is pointing in this direction to the west, and there is a much weaker jet which is pointing toward the east. Because Cygnus A is a very strong source, it took a lot of effort to bring out this weak jet, but in some other cases, it may not be the case. Okay, environment can play some role in the sense that what you're really talking about is dissipation of energy. So if the environment is asymmetric, that can also contribute to the asymmetry of the overall structure and the jet. But both these effects could play a role. Both these effects could play a role. But in the very smaller scale structures, for example, even this jet in 3C31, okay, which looks reasonably symmetric, that if you really look at it with very high resolution of the subarc second scale jet over here, which is not very obvious over here, you'll find it to be quite asymmetric. So in these cases, as the jets are moving out, the velocities are expected to be much higher, and it slows down as it dissipates energy. So these relativistic differences due to relativistic beaming effects will also go down when the velocities go down. So it is reasonable to assume that the difference which you're seeing here is probably largely due to the velocity of the jet rather than the environment. But the environment can play a role. where there could be more dissipation of energy by the jet which is encountering it, and leading to asymmetries in jet structures as well.
Thank you, sir.
Yeah. Okay, if there are no further questions, we could probably stop. I'll stop sharing the screen.